Welcome to Cornell Notes, the structure of the Earth and plate tectonics. This Cornell Note set will review structure of the Earth. However, you have already taken notes over Earth structure. Plate tectonics has a lot to do with the way the Earth is structured, so it's going to be good and it's actually going to be beneficial that we're kind of reviewing elements of the structure of the Earth. Please put your first and last name on your Cornell Notes, put today's date, put today's topic, and let's move forward. Okay, so a real quick review. The Earth is made up of three main layers: the core, the mantle, and the crust. The crust is where we live, and it is made up of it's either going to be continental crust or oceanic crust. Continental crust is thick. It is buoyant, meaning that it is less dense than the oceanic crust, and that's actually an important fact that you will see in slides that are upcoming. And it's mostly old. Your oceanic crust is thin, it's dense, and it sinks under the continental crust. And most of the time, your oceanic crust is going to be very young. Okay, I'm going to go ahead and move forward because, like I said, this is really a review. It's a review. So how do we know what the Earth is made of? Geophysical surveys, seismic activity, earthquakes, gravity, magnets. How do they get this information? Through the land, air, sea, and satellite. Also geological surveys such as fieldwork, boreholes, and mines. So this is really the meat of our new information. What are plate tectonics? If you look at this map, you're going to notice that a lot of the continents, they appear that they could fit together, similar to a puzzle. So I'm just going to give you a moment to look at that, kind of identify some places where you see that the continents could fit together. The Earth's crust is divided into 12 major plates, and they are constantly being moved in various directions. Plate motion will cause them to collide, pull apart, or scrape against each other. And that's what you're going to learn today. You're going to learn what geological formations occur or exist along these types of plate boundaries where colliding and pulling and scraping is actually taking place. So each one of these unique interactions causes a characteristic set of Earth structures or tectonic features. In some places, you will find rift valleys, underwater mountain ranges, and other places you'll find volcanoes. And if you've ever wondered why a volcano exists in the middle of the Pacific Ocean, you're going to learn that today too. Because there's not a plate boundary in the middle of the Pacific Ocean, but you're going to learn why that is. So the word tectonic refers to the deformation of the crust as a consequence of plate interaction. And you're also going to notice that Newton's third law plays a huge part in plate tectonics. So think back to what Newton's third law was. Every action has an equal and opposite reaction. Okay, and you're going to see that law throughout this entire note set. May I move forward? Remember, you don't have to read, or you don't have to write down every single word. Just write your keywords. Okay, on Monday, we are going to go over our world plates. We're going to do an activity. And you're actually going to need to bring your colored pencils because you're going to create a map that looks very similar to this. Right now, I just want you to look at it, kind of try to identify some plate names and why they are named what they are named. So I'm going to give you 7 to 10 seconds to look. Hopefully you've noticed that a lot of the plates, the earth plates, they are named after either the ocean or continents that they sit on. You'll notice that. So your Pacific plate sits on top of your Pacific Ocean. North American plate sits on top of North America. Now there are some weird ones. Look at this one, the Nazca plate. Okay, or like the Eurasian plate because it sits on top of Europe and Asia. Here we go back to review of Earth's structure. It's important that we cover this again because we're talking about plate movement. So let's talk about what the plates are made of. Please do not forget that our plates are made of what we call the lithosphere. And the lithosphere is made up of the crust, both oceanic and continental, and that upper part of the mantle. That is your lithosphere. That is actually what moves during plate tectonics during an earthquake. The tectonic plates is made up of the lithosphere. The lithosphere is made up of the crust and the upper part of the mantle. So what lies beneath the tectonic plates? Do you guys remember? The middle mantle, the asthenosphere. Very good. And remember what happens in the asthenosphere. Okay, what actually causes those plates to move? It's those convection cells, those convection currents, where really, 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 really hot magma will rise and, well, I hate to say cool magma, because magma is not cool, but I guess a cooler version of magma will sink, but it creates this convection cell. Okay, so if you are actually tested on a test, if you see what causes plates to move, the answer would be convection cells. So let's look at what happens at tectonic plate boundaries. This is where we're actually starting to build on some prior knowledge that you may have received in 6th grade or 7th grade. Hopefully this slide is a review. Okay, hopefully by 8th grade you are familiar with a divergent boundary, a convergent boundary, a transform boundary. And if not, that's okay. We're learning it again. We're reviewing it again. But in 8th grade, you actually learn the different geological structures that are created at each of these boundaries and why that happens. So at a divergent plate boundary, those two plates are pulling apart. Please make sure that you are drawing arrows. At a convergent boundary, the two plates are pushing together. And a lot of times at that boundary, one plate will slide underneath the other. And depending whether it's at a continental plate or continental or oceanic boundary, plate boundary, different things will happen at that convergent boundary. And then the last one is transform. Please draw your arrows. That's where the two plates actually slide past one another. And it can also be called strike slip. So you have divergent that pulls apart, convergent that pushes together, and transform, also called strike slip, where at the plate boundary, the plates slide past each other. Okay, I love this graphic. Let's look at it. Okay, we're specifically going to start talking about a divergent plate boundary right now. So right here, you've got two oceanic plates that are pulling apart. So you've got a divergent plate boundary between two oceanic plates. Okay, and it causes what's called a ridge. Okay, in the Atlantic Ocean, one of the longest mountain ranges in the world exists. It's called the Mid-Atlantic Ridge, and it's actually the longest mountain range in the world, but it's underwater. Okay, and it's formed because those two oceanic plates are pulling apart, and the convection currents allow the magma to rise. So essentially, there's like a volcano at the bottom of the ocean in the middle of the Atlantic, and it's just creating this underwater mountain range where the hot magma will rise. It cools. The igneous rock will cool very quickly because it's cold on the bottom of the ocean. And I like this. It says spreading ridges. As plates move apart, new material is erupted to fill the gap. Also, I want you to kind of just really quickly glance and look at what's happening between this oceanic plate and this continental plate right here. Just kind of look at that. Kind of see if you can figure out what's going on there. In a few slides from now, we're going to actually discuss that. But I did want to make you aware of that. If you look really carefully, you'll find the Mid-Atlantic Ridge right here. Do you see that? I want you to focus your attention right here. What is that? It's a continent, and the Mid-Atlantic Ridge is running straight through it. Okay, that's Iceland. Okay, and what's really interesting about Iceland, it is literally being ripped apart. It has a divergent plate boundary running straight through it. Okay, and so it creates what's called a rift valley. Can you write that, please? In Iceland, there is a rift valley. And it literally is a valley where the two plates are being pulled apart, and the land literally looks torn. Okay, it looks kind of like you've got this like valley, and then the land in between it, you see this like uplift, and it literally looks like it's being torn. Okay, and specifically what's going on there is the North American plate and the Eurasian plate are pulling apart along the Mid-Atlantic Ridge. That's mostly happening between oceanic crust and oceanic crust. But here on Iceland, that's continental crust and continental crust. So it creates the Rift Valley. Okay, let's talk about convergent boundaries, which are much, much, much more interesting, I think. Okay. These are your three different types of convergent boundaries, and it makes sense. You've got continental and continental collision. You've got continental and oceanic collision. And then you've got oceanic and oceanic collision. Now we're talking about the plates. So continental plates, oceanic plates. Different things happen along each of these. And you will be tested over this information. Can I move forward? See if you can hypothesize what the next slide is going to be. Okay, so when you have two continental plates that are colliding, it will form mountains. Put a star by that. Make sure you know that. Make sure you're studying that. When two continental plates collide, it'll form mountains. One plate will slide underneath the other and create uplift, or they could also collide together and push upward. But at either rate, they're pushing together and they're forming mountains. Continent to continent forms mountains. Okay, this is how the Himalayas were created. So you might want to put example Himalayas. Does anybody know where the Himalayas are located? What is it? Yeah. Okay. Okay, the next one is oceanic to continent, which does something really interesting. Okay, subduction. So this dense oceanic crust, it's actually going to slide under the continental crust. And the oceanic crust that is being subducted, it melts back into the mantle. And as it melts, the magma will rise, and a lot of times we'll create these like magma plumes that will rise up to the surface on the continental crust, and that's where you see a lot of volcanoes. Okay, this is what happens along the Ring of Fire. Okay. Also here, in this spot right here where I have my mouse, this oceanic crust that's being subducted, it scrapes against this continental crust, and it creates this like uplift right here from all that matter and material that's being scraped off. And then if you see right here, it also creates a little valley. Or sorry, not a valley, a trench. And we'll talk about that in a minute too. Okay? Continent to oceanic crust collision, subduction, that's where you're going to see a lot of your volcanoes. Okay, and this slide is just reinforcing what I've just explained to you. Oceanic lithosphere subducts underneath the continental lithosphere. The oceanic lithosphere heats and dehydrates. As it subsides, the melt rises, forming volcanism. So there it is. And an example would be the Andes. Let's go ahead and make sure that we write that. The Andes. But also remember, as these volcanoes ooze lava, they're creating new earth. So this mountain range, if it's got an active volcano, it could be getting higher and higher and higher. Okay, let's look at ocean to ocean plate collision. So when two oceanic plates collide, one will run over the other, which causes it to sink into the mantle, forming a subduction zone. The subducting plate is bent downward to form a very deep depression in the ocean floor called a trench. The world's deepest parts of the ocean are found along trenches, and an example is the Mariana Trench that is 11 kilometers deep. Does anyone know where the Mariana Trench is located? Okay, if you said south of Japan, you're right. Okay, so let's do an activity really quick. Put your pencil down, and I want you to push your fingers together. Okay, you're going to try to create quite a bit of pressure. Okay, you're going to subduct one hand under the other, and you're going to push very slowly and with quite a bit of pressure. Are you noticing how the subducting plate is bending downward? You seeing the V that's being created? See how there's like quite a bit of uplift and you've got your trench. Okay, that's essentially how a trench in the ocean is formed. Here's your Finding Nemo slide, right? Your anglerfish, okay, which can be found in some of the deepest parts of the ocean along those trenches. Okay, take a look right here. This is called the Puerto Rico Trench. Here you've got Cuba. You've got Puerto Rico. You've got your Caribbean plate over here. You've got your North American plate over here. This is along an oceanic crust to oceanic crust subduction zone, and it creates what we call the Puerto Rico Trench. And this is an example of a fish that can be found in that trench. Okay, let's talk about transform boundaries. So we're now looking at the third type of plate boundary. We looked at convergent boundaries. We looked at divergent boundaries. Now we're going to look at transform boundaries. One of the most famous transform boundaries in the world is the San Andreas Fault in California. Along the San Andreas Fault, those two plates, they slide past each other, and they constantly create earthquakes, which is why buildings in California have to be engineered to withstand earthquakes. Okay, so make sure you're drawing your arrows. There isn't anything that you need to write down for this slide. I just wanted you to look at it. You've got your different plates, and then you've got a key down here showing some plate boundaries. Divergent boundaries, transform, subduction zones, zones of extension within continents, and then also there are places where scientists are uncertain. Let's talk about volcanoes very quickly. Go ahead and write Ring of Fire. Volcanoes are mostly focused at plate margins or plate boundaries. And if you look back into your notes that you just took, you will see that most volcanoes are located along convergent boundaries where oceanic plates are subducting under continental plates. But I want you to look right here and notice that there are volcanoes in the middle of the plate. I wonder how that happened. Okay, so think about that for a second. Okay, so volcanoes are formed. Make sure you write these three things. Subduction, we already talked about that. Rifting, okay, which is exactly what's happening in Iceland. That's continent to continent crust. Oceanic to oceanic, the mid-Atlantic ridge. That's volcanic activity. And then also hotspots, which is going to be our next slide. So these are the three ways that volcanoes are formed. Subduction, rifting, so this is an example of rifting, and then hotspots. Okay, like I said, I want you to focus in right here, and I want you to notice that there is a hotspot in the middle of the Pacific Plate. Everything you've learned so far is that volcanoes exist along plate boundaries. Well, how does that happen? It's in the middle of the Pacific. There's no plate boundary there. Okay, it's because there is a hot spot in the middle of the Pacific Ocean. So let's go ahead and make sure that we take some notes over hot spots. The hot mantle plumes actually breach the surface in the middle of a tectonic plate. That is the definition of a hot spot. A hot mantle plume will breach the surface in the middle of a tectonic plate. And the Hawaiian Islands, that chain of Hawaiian Islands, are examples of hotspot volcanoes. And what you're going to see in the next slide is that the hotspot doesn't move, but the plate does. And that's actually what creates the island chain. Can I move forward? So make sure you write hotspot volcano. Mantle plume breaches surface in the middle of a tectonic plate. Example, Hawaii. And you might even want to include the words island chain. Okay, so let's look at this graphic very quickly. It says the volcanoes get younger from one end to the other. Okay, so here's the youngest volcano. It's active. It's sitting on top of a current hotspot. The magma will rise, and it's creating new land. Actively creating new land. But what has happened over time is the oceanic crust has moved due to plate tectonics. So you see this island right here? He was formed because he actually used to sit on top of that same hotspot. And this island was formed because he used to sit on top of this hotspot. So here you've got youngest, second youngest, oldest. And what's really is interesting about this is as this island is being created, these two islands, well this one also, but these two islands are being destroyed by erosion, by weathering and erosion. So sometimes they get smaller and smaller. We're almost done, guys. Just remember that volcanoes and earthquakes are not randomly distributed. Okay, they do not happen at random. Where do they happen? Along plate boundaries or even on hotspots, yeah. Okay, and this is going to be your last slide. I want to kind of use this as somewhat of a review. Okay, let's look at it. Here you've got oceanic to oceanic crust at a divergent boundary. Think about what happens there and what is formed. Hopefully you said a mid-Atlantic ridge. Okay. Here you've got a trench that is being created when continental crust and oceanic crust collide and the oceanic crust slides underneath. Don't forget that subducting slab, as it's melted, that magma will rise and often create volcanoes on the crust of the earth. And that is all I've got for you guys. So take a look at that summary. Thank you for taking Cornell notes with me.